In 1963, one tiny particle kept choosing the harder way to die. Physicists called it the phi meson. It had enough energy to break into a rho meson and a pion, and that should have been the easy route. Instead, that decay happened about 100 times less often than expected. The phi preferred to become two heavier particles called kaons, even though that route left almost no energy to spare. George Zweig stared at this backward result and made a dangerous choice. He assumed the experiment was telling the truth. If the phi preferred the cramped doorway, perhaps it was carrying something through that doorway, something hidden inside the particle itself. That is the first strange thing about this story. The clue was not a new particle flashing into existence. It was an absence, a decay that should have happened but almost never did. To use that silence, Zweig had to stop treating a particle as a featureless point and ask what might be rearranging inside it. That possibility cut against the way many physicists pictured nature. Protons, neutrons, and dozens of newly discovered particles were treated as members of a complicated family, but not necessarily as containers with smaller objects inside. Zweig proposed that they were built from fundamental constituents with fractional electric charges. He called them aces. At almost the same moment, Gell Mann independently proposed related constituents and gave them the name that survived, quarks. Today, every proton in your body is understood through that deeper structure. But in 1964, a particle carrying 1/3 of an electric charge sounded less like an answer than a new impossibility. What did Zweig see in that strange decay that everyone else's equations had missed? The stakes went beyond naming another subatomic object. If the model was right, the supposedly elementary proton was built from pieces. The bottom floor of matter had another floor underneath it. Zweig had just finished doctoral work at Caltech, where Richard Feynman had been one of the strongest influences on him. Feynman was not someone a young theorist ignored casually. When Zweig brought him the strange phi decay, Feynman suspected the measurement or the interpretation had to be wrong. The objection was serious. In strong interaction physics, states with the same quantum numbers could mix. The rho pion and kaon antikaon outcomes seem to carry the same overall labels. Why should nature sharply distinguish one route from the other? To Feynman, forbidding the easier decay threatened a basic principle called unitarity, and the experimental situation was young enough that a bad measurement was entirely plausible. Detectors were reconstructing brief tracks from particles that vanished almost as soon as they appeared. Betting a new layer of nature on one surprising branching pattern could ruin a young theorist's credibility. Zweig knew that Feynman's doubts were reasonable. He also remembered an earlier occasion when ignoring advice had ended badly. This time, though, the pattern would not let him go. The phi decayed into kaons with a huge signal right at the edge of what energy allowed. The supposedly easier rho pion route remained suppressed. He asked a more physical question. What if those final particles were not interchangeable packages? What if each one carried particular ingredients? A decay that preserved the ingredients already inside the phi could happen readily. A decay that destroyed them and manufactured different ones could be rare. The strange data stopped looking like an error. It started looking like an inventory. This was the move that separated Zweig's picture from a purely abstract classification. He wanted to know what the particles were made of and how those parts moved through an actual reaction. The bookkeeping had to describe a physical mechanism. During a visit to CERN, Zweig turned that inventory into a model. He proposed 3 basic aces. Baryons, the family containing protons and neutrons, were made from 3 aces. Mesons were made from an ace and an anti-ace. Different combinations produce particles with different electric charge, mass, and strangeness. The arithmetic was startling. The constituents had fractional charges. One type carried positive 2/3 of the electron's charge unit. 2 others carried negative 1/3. Put 2 positive 2/3 constituents with 1 negative 1/3 constituent, and the total is +1, the charge of a proton. Rearrange them and the total can become 0, the charge of a neutron. The same small set could be recombined again and again. What looked like dozens of unrelated particles became variations built from a few pieces, much as many words can be assembled from a small alphabet. The model did not remove the complexity of the strong force, but it moved that complexity from the list of particles into the rules connecting their constituents. No detector had ever collected a loose particle with 1/3 of a charge. Yet the fractions vanished inside the combinations we actually observe. 3 aces could sum to an ordinary integer-charged baryon. An ace paired with an anti-ace could do the same for a meson. Antimatter made the accounting work in the other direction. An anti-ace carried opposite charge and opposite additive quantum numbers. Pairing an ace with an anti-ace allowed a meson to have 0 or integer charge while still keeping a distinct internal identity. Zweig chose the name because he did not know how many constituents nature might require. 4 leptons were known, so he imagined that a 4th ace might eventually appear, like the 4 aces in a deck. His first working model used 3. The name was playful, but the claim was concrete. These were not merely symbols for sorting particles. They had mass, spin, binding energy, and dynamics inside the objects they built. Now return to the phi. In modern language, it is dominated by a strange quark and a strange antiquark. A kaon contains one strange constituent or its antimatter partner. When the phi becomes a kaon and antikaon, its hidden ingredients can flow into the products. Nothing essential has to vanish. The rho, meson, and pion contain different light constituents. To reach that outcome, the strange pair inside the phi must annihilate and new light constituents must appear. The total quantum numbers may match, but the internal root is not the same. That makes the rho-pion decay far less likely. It is like watching a locked case pass through one doorway intact, but fail at another doorway that looks wider. The outside dimensions are not the deciding factor. The contents and the way they must be repacked control the result. This idea did more than rescue one odd decay. The same constituent assignments produced accurate relationships among the masses of several vector mesons. One hypothesis explained the suppressed channel, organized particle families, and predicted numerical patterns. The crowded particle zoo began to look less like a collection of fundamental species and more like a cabinet of combinations. A proton and neutron were not lonely exceptions at the base of matter. They were arrangements of a smaller alphabet. In January 1964, Zweig wrote the first of 2 long CERN reports describing that alphabet and suggesting experiments that might find the aces themselves. His diagrams made the claim visible. Mesons contain 2 constituent marks connected together. Baryons contained 3. The lines were not decorative. They announced that the constituents belonged inside a bound object and that the structure of that object governed what it could become. Zweig was not alone. At Caltech, Murray Gell-Mann reached a related 3-constituent scheme independently. His short paper introduced the word quark, borrowed from a line in James Joyce. Gell-Mann emphasized the mathematical symmetry that organized the hadrons. Zweig emphasized concrete constituents moving inside them. Those differences mattered in 1964, but the later theory grew from ideas on both sides. This is not a story about one man stealing another man's discovery. It is a story about parallel insight, unequal visibility, and a scientific community unsure whether the new object should be taken literally. The timing was extraordinarily close. Zweig's first report is dated January 17th. Gell-Mann's paper appeared in the same season. Nature had offered the same puzzle to 2 theorists with overlapping intellectual roots, and they pulled out related answers from different directions. Zweig's treatment was extensive. His second CERN report ran to roughly 80 pages and worked through masses, couplings, decays, and possible searches. It circulated as a preprint rather than becoming the famous compact journal paper that defined the idea for most readers. The reaction was mixed and sometimes harsh. In later recollections, Zweig said one prominent theorist called the ACE model the work of a charlatan. But skepticism was not irrational. Fractional charge was unprecedented. The model raised problems about particle statistics. Most damaging of all, experiments searched for free fractionally charged objects in accelerators, cosmic rays, seawater, and other materials. They found none. Every failed search sharpened the dilemma. Either the constituents were not real, or nature had invented a kind of prison unlike anything physicists understood. A useful classification could survive without literal particles. A physical model needed to explain why its pieces were permanently missing from the laboratory bench. If quarks were real, why could nobody pull one out? For a time, some physicists treated them as useful mathematical bookkeeping, Then a 2-mile electron accelerator at Stanford supplied a new kind of microscope. Beginning in 1967, teams from SLAC and MIT fired high-energy electrons at protons and neutrons. At first, they studied collisions in which the target stayed intact. Then they measured deep inelastic scattering, violent impacts where the proton broke apart. They expected a soft, diffuse target. Instead, far more electrons bounced through large angles than anticipated. The accelerator was nearly 2 miles long because resolution at this scale comes from energy. A faster electron carries a shorter effective wavelength and can probe smaller structure. The team measured both the scattered electron's angle and its remaining energy, reconstructing what it had struck without ever photographing a quark. The pattern resembled Rutherford's old discovery of the atomic nucleus. A probe that should pass through something soft occasionally struck a hard point. Inside the proton were compact scattering centers. Richard Feynman called them partons. Further theory and experiment connected those partons with quarks. The missing free particles now required a different explanation. In quantum chromodynamics, quarks carry a new kind of charge called color. Gluons transmit the strong interaction. Pulling quarks apart does not weaken the connection the way separating electric charges does. The energy in the field grows until it is easier to create new quark-antiquark pairs, which bind into new particles. The quark leaves tracks everywhere, but never walks out alone. That is why a collider produces sprays called jets rather than a neat, isolated, fractionally charged dot. The departing quark starts a cascade. Energy becomes more quarks and antiquarks, and those pieces lock themselves into ordinary hadrons before reaching the detector. By the 1970s, the quark model had become part of a larger theory of the strong force. The discovery of the J/psi particle in 1974 revealed a bound charm quark pair and helped make the quark picture unavoidable. The vocabulary settled around quarks, not aces. Zweig eventually moved into neurobiology, studying how sound is represented and how the inner ear works. That shift did not erase his contribution. Historical accounts now routinely credit Gell Mann and Zweig as independent originators of the quark model, while also recognizing the experimental teams and theorists who turned the proposal into modern particle physics. The proton under your hand is not three little marbles sitting still. It is a quantum storm of valence quarks, gluons, and short-lived quark-antiquark pairs. Yet its overall identity still reflects the constituent pattern that Zweig and Gell Mann saw in the particle zoo. Most of the proton's mass does not come from simply adding the bare masses of three valence quarks. It emerges from the energy of the strong field and the restless motion inside. The model opened the door, but the room beyond it was richer than the first drawings could show. One stubborn decay opened the door. The phi chose the route that preserved its hidden ingredients, and a young physicist trusted that clue enough to imagine matter beneath matter. If you want more stories where one impossible measurement exposes a new layer of nature, subscribe. And tell me in the comments which is stranger, a particle with 1/3 of a charge, or a force that never lets you hold it by itself.